Life on Comets and Asteroids, a meditative journey through cosmic wanderers. In the vast expanses between worlds, where sunlight grows thin and temperatures plunge toward absolute zero, there drift countless wanderer-sentient fragments of cosmic creation that have journeyed through space since the birth of the solar system. These comets and asteroids, often dismissed as mere rocks and ice, may harbor one of the universe's most profound secrets, the delicate spark of life itself, persisting in conditions that challenge every assumption about where biology can flourish. The possibility of life on these cosmic nomads transforms our understanding of existence from something precious and rare to something resilient and adventurous, capable of making homes in the most unlikely places. These celestial bodies, born in the chaotic early days of planetary formation, carry within their cores the pristine materials from which all worlds emerged. They are time capsules and seed banks, libraries of cosmic chemistry, and perhaps nurseries of biological innovation. As consciousness settles into contemplation of these wandering worlds, there emerges a profound sense of life's tenacity and creativity. The organisms that might exist on comets and asteroids would represent evolution's most extreme experiments, life forms adapted to conditions of perpetual cold, minimal energy, and the vast loneliness of interplanetary space. Their existence would suggest that biology is not merely an accident of favorable conditions, but a fundamental expression of the universe's creative potential. These cosmic wanderers invite reflection on the nature of home and belonging, on how life might create meaning and purpose in environments that seem utterly hostile to existence. The microorganisms that might dwell within asteroid cores or beneath cometary ice would experience reality in ways that stretch the imagination, living in slow motion through cosmic winters that last millions of years, awakening to brief periods of activity when their worlds approach the warmth of stars, existing in communities so sparse and patient that they redefine the meaning of biological time. In this exploration of life on comets and asteroids, the mind finds a gentle rhythm that mirrors the slow dance of these objects through space, their patient journeys through the darkness, punctuated by moments of illumination and warmth. Their stories become meditations on endurance, adaptation, and the possibility that life is not confined to the surfaces of planets but permeates the cosmos itself, finding ways to flourish wherever chemistry allows and time permits. The ancient archives of space, deep within the asteroid belt that separates Mars from Jupiter, and in the distant reaches of the Kuiper belt beyond Neptune, there exist countless fragments of the solar system's earliest days' rocky remnants and icy visitors that preserve within their cores the pristine materials from which planets formed over 4.5 billion years ago. These cosmic archives carry within their structure not merely the elements of life, but the very conditions that may have nurtured its first emergence. Asteroids, those metallic and rocky wanderers, formed in the inner regions of the early solar system, where temperatures were high enough to prevent the condensation of volatile compounds. Yet within their interiors, protected from the harsh radiation of space and the violence of cosmic collisions, there exist microenvironments where liquid water might persist for millions of years. The decay of radioactive elements within asteroid cores generates heat that can melt ice trapped in rocky matrices, creating hidden oceans that remain liquid even in the frigid void of space. These internal seas represent some of the most stable aquatic environments in the solar system, insulated from the temperature fluctuations that affect planetary surfaces and protected from the cosmic radiation that sterilizes exposed surfaces. Within these dark waters, dissolved minerals create chemical gradients that could drive the same metabolic processes that sustain life in Earth's deep ocean trenches. The slow circulation of these hidden waters, driven by the gentle heat of radioactive decay, creates currents that could distribute nutrients and energy throughout the asteroid's aquatic core. The discovery of organic compounds within meteorites fragments of asteroids that have fallen to Earth reveals that these cosmic wanderers carry complex carbon-based molecules that serve as the building blocks of biological series systems. Amino acids, the components of proteins, exist within meteoritic samples in forms that suggest they formed through natural chemical processes in space rather than contamination from terrestrial sources. These compounds demonstrate that the chemistry of life operates throughout the cosmos, creating biological precursors in environments far removed from planetary surfaces. Some asteroids contain clay minerals that form only in the presence of liquid water, providing direct evidence that these bodies once harbored aquatic environments where chemical evolution could proceed along pathways that might lead to biological organization. The presence of these hydrated minerals suggests that water has flowed within asteroid interiors for extended periods, creating the stable chemical conditions necessary for the complex molecular interactions that precede the emergence of life. The gravitational interactions between asteroids and planets create tidal forces that can generate additional heat within these rocky bodies, extending the periods during which internal waters remain liquid. As asteroids pass near massive planets during their orbital journeys, the gravitational stress flexes their internal structure, converting mechanical energy into thermal energy that maintains aquatic environments for extended periods. These tidal heating episodes create windows of increased biological activity that might persist for thousands or millions of years. The metallic composition of some asteroids provides another pathway for life-supporting chemistry through the generation of hydrogen gas via the reaction between water and iron-rich minerals. This process, similar to serpentinization reactions that occur on Earth and potentially on other worlds, creates reducing environments where primitive metabolisms might extract energy from chemical gradients rather than sunlight. The slow oxidation of metallic cores could sustain biological communities for geological timescales. The diverse composition of asteroid populations from carbonaceous chondrites, rich in organic compounds, to metallic asteroids, composed primarily of iron and nickel, creates a spectrum of chemical environments that might support different forms of life adapted to specific mineralogical conditions. Each type of asteroid represents a unique biological experiment, a distinct set of chemical constraints within which evolution might explore different solutions to the challenges of existence in space. The formation history of asteroids, involving repeated cycles of heating, cooling, collision, and reassembly, creates complex internal structures with multiple microenvironments that could support diverse biological communities. Fracture networks within asteroid interiors provide pathways for chemical transport and energy flow, creating interconnected habitats that might sustain ecosystem-level interactions despite the extreme isolation of their cosmic setting. The longevity of asteroids objects that have remained largely unchanged for billions of years provides the extended timescales necessary for the slow chemical evolution that might precede biological emergence. Unlike planetary surfaces, which undergo constant change through geological and atmospheric processes, Asteroid interiors represent stable laboratories where chemical experiments can proceed uninterrupted for cosmic ages. Now, close the eyes and drift toward these ancient wanderers, imagining the dark waters hidden within their rocky hearts, where chemistry dances slowly in the eternal night, where molecules gather and organize in patterns that whisper of life's possibility. The nomadic gardens of ice, far beyond the asteroid belt, in the cold outer reaches of the solar system, there dwell the comet's ancient repositories of ice and dust that formed in the frigid regions where gas giants condensed from the primordial solar nebula. These icy wanderers carry within their frozen cores the preserved chemistry of the early solar system, along with the potential for biological communities that could survive the long journey through interstellar space. Comets represent time capsules from the solar system's birth, their composition largely unchanged since they condensed from the disk of gas and dust that surrounded the young sun. Within their nuclei, water ice mingles with frozen carbon dioxide, methane, and ammonia, creating a chemical environment rich in the compounds necessary for biological processes. The organic molecules embedded within cometary ice include complex carbon-based structures that form naturally through radiation-induced chemistry in the cold depths of space. The internal structure of comet nuclei creates microenvironments where liquid water might exist even at temperatures far below the normal freezing point. The presence of dissolved salts and organic compounds can significantly lower the freezing point of water, creating brines that remain liquid at temperatures approaching -40 degrees Celsius. These concentrated solutions could support biological processes adapted to high salinity, low temperature conditions, similar to those found in Earth's most extreme environments. The gentle heating that occurs when comets approach the inner solar system transforms these icy bodies into dynamic worlds where liquid water flows beneath sublimating surfaces. As solar radiation warms the comet nucleus, subsurface ice melts to create temporary aquatic environments that could support increased biological activity during these brief periods of relative warmth. These thermal episodes might trigger dormant biological processes, allowing cometary life to complete reproductive cycles during favorable conditions. The layered structure of comet nuclei, built up through countless orbits and multiple episodes of ice accretion, creates distinct zones with different chemical compositions and thermal properties. These layers preserve records of changing conditions in the outer solar system while providing diverse habitats where different forms of life might have evolved to exploit specific chemical environments. The interface between layers could create chemical gradients that drive metabolic processes. The organic chemistry of comets extends far beyond simple molecules to include complex macromolecular structures that approach the complexity of biological polymers. Spectroscopic observations of comet atmospheres reveal the presence of formaldehyde, methanol, and hydrogen cyanide compounds that serve as precursors to amino acids and nucleotide bases under appropriate conditions. The radiation environment of space drives continuous chemical evolution within cometary ice, creating increasingly complex molecular structures over cosmic timescales. The discovery of amino acids within samples from Comet Wild 2, returned by the Stardust mission, provides direct evidence that these icy bodies contain the molecular building blocks of proteins. The presence of both left-handed and right-handed versions of these molecules, in ratios different from those found in terrestrial biology, suggests that cometary organic chemistry follows its own evolutionary pathways independent of planetary processes. The magnetic properties of some comets indicate the presence of metallic grains within their nuclei, creating environments where electromagnetic chemistry could drive biological processes. The interaction between solar wind particles and these embedded metals could generate electrical currents within cometary ice, providing energy sources for chemosynthetic metabolism that operates independently of photosynthesis or chemical gradients. The periodic nature of cometary orbits creates cycles of heating and cooling that might drive evolutionary pressures on any biological communities within these icy worlds. Organisms adapted to cometary environments would need to survive extended periods of dormancy during the cold phases of their orbit, while taking advantage of brief warm periods to complete essential biological processes. This cyclical environment might favor life forms with extraordinary longevity and patience. The fragmentation of comets through tidal forces or collision events could serve as a mechanism for biological dispersal, spreading life-bearing fragments throughout the solar system and potentially to other stellar systems. Each fragment would carry with it the biological heritage of the parent comet while beginning its own independent journey through space. This process could explain how life might spread between worlds and even between star systems. The diverse population of comets, from short-period visitors that return every few years to long-period wanderers with orbital periods measured in millions of years, provides a spectrum of environments and evolutionary timescales for biological development. Each cometary population represents a different biological experiment, exploring different strategies for survival in the cosmic environment. The chemistry of survival within the frozen hearts of comets and the rocky cores of asteroids. Chemistry operates under conditions so extreme that they redefine the boundaries of what seems possible for biological processes. The organisms that might exist in these environments would represent evolution's most creative solutions to the challenges of survival in near absolute zero temperatures, minimal energy availability, and isolation from the continuous chemical cycling that characterizes planetary environments. The biochemistry of life in these cosmic wanderers would necessarily differ from terrestrial biology in fundamental ways. Adapted to environments where water exists primarily as ice or highly concentrated brine, where energy sources are scarce and intermittent, and where the pace of chemical reactions slows to nearly imperceptible rates. These organisms would exist in a state of suspended animation for most of their existence, their metabolic processes operating so slowly that millions of years might pass between significant biological events. The energy sources available to life on comets and asteroids come primarily from chemical gradients created by radioactive decay, cosmic radiation, and the slow oxidation of metallic minerals. Unlike the abundant solar energy that drives terrestrial ecosystems, these energy sources provide only tiny amounts of power that must be carefully conserved and efficiently utilized. Organisms adapted to these conditions would have evolved metabolic pathways capable of extracting maximum energy from minimal chemical differences. The formation of organic molecules within these cosmic environments follows pathways that involve the interaction of simple compounds with cosmic radiation over extended timescales. High-energy particles from space gradually transform basic carbon compounds into increasingly complex structures, creating a slow but steady supply of organic building blocks. This radiation-driven chemistry operates continuously, even in the coldest environments, providing a foundation for biological complexity. The preservation of organic compounds within the frozen matrices of comets and asteroids creates chemical libraries that accumulate complexity over cosmic timescales. Unlike planetary environments where organic molecules are constantly recycled through biological and geological processes, these cosmic repositories allow complex compounds to accumulate without degradation, creating chemical diversity that might eventually cross the threshold into biological organization. The role of catalytic surfaces within these environments cannot be overlooked. Mineral grains within asteroid cores and comet nuclei provide surfaces where chemical reactions can proceed more efficiently than in purely aqueous solutions. These mineral catalysts could facilitate the formation of complex organic polymers and might even serve as templates for the replication of primitive genetic materials. The diversity of mineral compositions within these bodies creates multiple catalytic environments where different aspects of prebiotic chemistry might flourish. The extremely low temperatures that characterize these environments actually favor certain types of chemical stability, allowing complex molecular structures to persist for extended periods without thermal degradation. Proteins and nucleic acids that would rapidly denature under terrestrial conditions might remain stable for millions of years in the frozen environment of a comet nucleus, creating the possibility for biological information to be preserved across cosmic timescales. The cyclic nature of comet orbits creates opportunities for accelerated chemistry during warm periods when liquid water becomes available and reaction rates increase significantly. These brief episodes of enhanced activity might allow dormant biological systems to complete essential processes like reproduction or DNA repair before returning to their suspended state. The timing of these cycles, measured in years to centuries for different comets, would shape the evolutionary strategies of any organisms adapted to these environments. The chemical diversity within and between different cosmic bodies creates the possibility for horizontal gene transfer between widely separated populations. When fragments of asteroids or comets collide and exchange material, they might also exchange genetic information, creating opportunities for biological innovation that transcends the boundaries of individual worlds. This cosmic-scale genetic mixing could accelerate evolution despite the extremely slow pace of individual metabolic processes. The alkaline conditions that develop within some carbonaceous asteroids, created by the interaction of water with specific mineral assemblages, provide environments chemically similar to those proposed for the origin of life on Earth. These high pH conditions favor the formation of RNA-like molecules and could support the development of primitive genetic systems based on ribonucleic acid chemistry. The protective environment within these cosmic bodies shields potential biological systems from the harsh radiation of space, while allowing sufficient cosmic ray penetration to drive ongoing chemical evolution. This balance between protection and activation creates conditions where life might slowly evolve and persist without being sterilized by excessive radiation or starved by complete isolation from energy sources. Now, let consciousness settle into the rhythm of this patient chemistry, where molecules dance in slow motion through cosmic time, where life might emerge, not through dramatic transformation, but through the gentle accumulation of chemical complexity over millions of years. If this gentle vision of the cosmos soothes the mind, consider resting here more often. Subscribe to the channel and share your thoughts in the comments. A quiet echo beneath the stars, the slow dance of extremophiles. In the hidden aquatic realms within asteroid cores and beneath cometary ice, life would exist at a pace so different from terrestrial biology that it challenges fundamental assumptions about the nature of living processes. The extremophiles that might inhabit these cosmic environments would represent the ultimate expression of biological patience, existing in communities where individual organisms might live for millions of years while biological processes unfold at rates measured in geological time. These cosmic extremophiles would belong to categories of life that push the boundaries of what Earth-based biology considers possible. Psychrophiles adapted to temperatures approaching absolute zero would possess biochemical mechanisms for maintaining cellular function when the kinetic energy of molecules drops to near minimum values. Their enzymes would operate through quantum mechanical effects rather than classical thermal motion, catalyzing reactions at rates thousands of times slower than their terrestrial counterparts. The cellular architecture of these organisms would necessarily differ from conventional biological designs, incorporating antifreeze proteins and specialized membranes capable of maintaining integrity at extremely low temperatures. Their cell walls might contain unique compounds that remain flexible even when water crystallizes, preventing the mechanical damage that typically destroys cells during freeze-thaw cycles. These adaptations would allow them to survive repeated transitions between frozen and liquid states as their host bodies experience orbital variations. The reproductive strategies of cosmic extremophiles would reflect the extreme constraints of their environment, where energy is scarce and opportunities for active metabolism are rare. These organisms might reproduce only during the brief, warm periods of their host body's orbit, synchronizing their life cycles with cosmic mechanical cycles that span years or decades. Their reproductive cells would need to survive extended dormancy periods while retaining the ability to resume development when conditions become favorable. The metabolic pathways employed by these organisms would exploit chemical energy sources unavailable to most terrestrial life forms. Radiotrophic metabolism, deriving energy directly from cosmic radiation, would allow these organisms to maintain basic cellular functions even in the absence of chemical gradients. This form of metabolism, observed in certain Earth-based extremophiles exposed to high radiation environments, could be amplified in cosmic settings where radiation provides the primary energy input. The community structure of these biological systems would operate at scales and timescales that dwarf terrestrial ecosystems. Individual microorganisms might be separated by distances measured in meters or kilometers, communicating through chemical signals that propagate slowly through frozen or briny media. The concept of a biological community would extend across the entire volume of their host asteroid or comet, creating ecosystems with dimensions measured in planetary scales. The evolutionary timescales available to these organisms would allow for biological innovations impossible under terrestrial conditions. With lifespans potentially measured in millions of years, individual organisms could accumulate genetic changes through direct mutation and selection over timescales that encompass entire planetary evolutionary epochs. This extended temporal perspective might allow for evolutionary experiments that explore biological possibilities unavailable to shorter-lived organisms. The dispersal mechanisms for these cosmic life forms would operate through processes unique to the space environment. When asteroids fragment through collision or tidal disruption, the resulting debris could carry living organisms to new environments throughout the solar system. This biological dispersal would occur at velocities measured in kilometers per second, potentially allowing life to spread between widely separated celestial bodies within cosmically brief timescales. The information processing capabilities of these organisms would reflect their environment's extreme constraints on energy and time. Their genetic systems might employ error correction mechanisms that operate over extended timescales, gradually repairing radiation damage while preserving essential biological information. Their molecular machinery would operate with extraordinary efficiency, maximizing information processing while minimizing energy expenditure. The sensory systems of cosmic extremophiles would detect environmental changes that occur over timescales measured in years or decades. These organisms might sense the approach of perihelion, the closest point in their orbit to the sun, months or years in advance, beginning physiological preparations for increased thermal activity. Their biological clocks would operate on astronomical timescales, synchronized with orbital mechanics rather than daily or seasonal cycles. The biochemical diversity within populations of cosmic extremophiles would reflect the chemical diversity of their environment, with different organisms specialized for different mineral associations or chemical gradients within their host body. This metabolic specialization would create biological communities where different species exploit different aspects of the available chemical energy, creating ecosystem-level organization despite the extreme sparsity of individual organisms. The genetic exchange mechanisms employed by these organisms would operate through processes adapted to their dispersed spatial distribution and extended temporal cycles. Horizontal gene transfer might occur through the exchange of genetic material during rare collision events, or through the gradual diffusion of genetic elements through the aquatic media that connects distant biological communities within their host body. The wandering gardens between worlds. As asteroids and comets journey through the vast spaces between planets, they carry with them their hidden biological cargo, creating a network of life that spans the entire solar system. These wandering gardens represent a form of biological organization that transcends the boundaries of individual worlds, connecting distant regions of space through the patient migration of living systems that persist across cosmic voyages measured in millions of years. The orbital dynamics of these cosmic wanderers create complex patterns of biological exchange as their paths intersect and diverge over astronomical timescales. When asteroids approach planets during their elliptical journeys, gravitational interactions can alter their trajectories, sending them toward new regions of the solar system where they might encounter different populations of cosmic life. These gravitational encounters serve as mixing events that could drive biological diversity across the entire system. The long-period comets that visit the inner solar system carry biological heritage from the distant Oort cloud, that spherical shell of icy bodies that extends halfway to the nearest stars. These visitors bring with them the chemical and potentially biological legacy of the solar system's formation, preserved in pristine condition for billions of years in the deep freeze of interstellar space. Their rare appearances in the inner system create opportunities for biological exchange between the most distant and closest regions of solar space. The concept of panspermia, the transfer of life between worlds, finds its most plausible expression in the patient journeys of asteroids and comets. Unlike the dramatic scenarios of rocks blasted from planetary surfaces by impact events, these cosmic wanderers provide stable, protected environments where biological systems can survive interplanetary voyages lasting millions of years. Their internal aquatic environments shield living organisms from the lethal radiation of space while providing the chemical resources necessary for survival during extended journeys. The capture of interstellar objects by the solar system's gravitational field occasionally introduces visitors from other stellar systems, potentially bringing with them biological heritage from distant worlds. The recent detection of interstellar asteroids passing through the solar system demonstrates that exchange between stellar systems occurs regularly, creating opportunities for biological transmission across interstellar distances over cosmic timescales. The fragmentation of comets and asteroids through tidal forces or collision events creates swarms of smaller bodies that disperse throughout the solar system, each carrying a sample of their parent body's biological content. This fragmentation process multiplies the number of potential biological habitats while distributing life-bearing material across wider regions of space. The resulting debris streams create networks of related biological communities spread across multiple orbital zones. The seasonal variation in comet activity as these bodies approach and recede from the Sun creates rhythmic patterns of biological activity that pulse throughout the solar system. During perihelion passages, comets release not only gas and dust but potentially biological materials that could survive brief exposure to space before being deposited on planetary surfaces or captured by other cosmic bodies. These episodic releases create opportunities for biological seeding across multiple worlds. The interaction between cosmic wanderers and planetary magnetospheres during close approaches creates complex electromagnetic environments where charged biological particles might be captured and guided toward planetary surfaces. The magnetic fields of planets could serve as funnels that concentrate biological material from passing asteroids and comets, creating focused delivery mechanisms for cosmic life to seed planetary environments. The gravitational resonances that govern the long-term orbital evolution of asteroids and comets create stable pathways through the solar system where biological material could be reliably transported between different regions. These resonant chains connect the asteroid belt with the Trojan asteroids of Jupiter, the Centaur objects between Jupiter and Neptune, and the trans-Neptunian populations, creating highways for biological dispersal that operate over geological timescales. The thermal evolution of these cosmic bodies as they age creates changing environmental conditions that might drive biological evolution in response to gradually shifting chemical and physical constraints. As radioactive elements decay and thermal energy decreases, the aquatic environments within these bodies would gradually cool and concentrate, creating evolutionary pressures that favor organisms adapted to increasingly extreme conditions. The cosmic ray environment that pervades interplanetary space provides a constant source of ionizing radiation that could drive mutation and genetic diversification in biological populations during their cosmic journeys. This radiation-driven evolution might accelerate the development of new biological capabilities, allowing cosmic life to adapt to the unique challenges of existence in space environments. The dust and gas trails left by comets during their orbital passages create extended environments where biological materials might persist in dispersed form, creating tenuous biological clouds that connect different regions of the solar system. These particle streams could serve as repositories for biological information and genetic material that remains viable for extended periods in the cold vacuum of space. Now, envision these cosmic gardens drifting through the darkness, each carrying its secret cargo of life across the vast distances between worlds, creating connections that span the entire solar system through the patient journeys of living systems adapted to the ultimate frontier, the deep time of cosmic evolution. The biological processes that might unfold within comets and asteroids operate on timescales that dwarf terrestrial evolution, creating opportunities for biological development that transcend the constraints of planetary environments. The cosmic wanderers that carry life through space provide laboratories for evolutionary experimentation, where biological systems can explore possibilities unavailable to organisms confined to single worlds. The extended lifespans available to organisms in these environments, potentially measured in millions of years for individual microorganisms, create opportunities for biological complexity to emerge through mechanisms impossible under terrestrial conditions. Single organisms might accumulate thousands of generations of genetic material through endosymbiosis or viral integration, gradually incorporating the biological innovations of entire ecosystems within individual cellular structures. The isolation of biological populations within different cosmic bodies creates evolutionary laboratories where life can explore different solutions to fundamental biological challenges without interference from competing populations. Each asteroid or comet becomes an independent biological experiment, testing different metabolic strategies, reproductive mechanisms, and survival techniques over cosmic timescales. The results of these experiments eventually mix when cosmic bodies interact, creating opportunities for biological innovation through the exchange of evolutionary discoveries. The chemical evolution that continues within these cosmic environments provides a constantly changing backdrop for biological development. The ongoing production of complex organic molecules through radiation-induced chemistry creates new chemical possibilities for biological systems to exploit, while the gradual depletion of certain compounds through biological processes drives evolutionary pressure toward increased efficiency and novel metabolic pathways. The cosmic radiation environment that pervades space creates mutation rates and selective pressures unlike those found in planetary environments. The high-energy particles that constantly bombard these cosmic bodies drive genetic diversification while simultaneously creating selection pressure for enhanced radiation resistance. This radiation-driven evolution might favor biological systems with redundant genetic mechanisms and enhanced DNA repair capabilities. The thermal cycles experienced by these bodies as they follow elliptical orbits create rhythmic environmental changes that could drive evolutionary development over astronomical timescales. Organisms adapted to these cosmic rhythms would evolve biological clocks synchronized with orbital mechanics, developing life cycles that span years or decades while maintaining genetic continuity across multiple thermal cycles. The gravitational interactions between cosmic bodies create opportunities for biological exchange that might accelerate evolutionary development through horizontal gene transfer between widely separated populations. When asteroids experience close encounters or collision events, they might exchange biological material along with physical debris, creating opportunities for genetic recombination between organisms that evolved in isolation for millions of years. The discovery that some meteorites contain complex organic structures that approach the complexity of primitive cells suggests that the transition from chemical to biological organization might occur naturally within cosmic environments, given sufficient time and appropriate conditions. The identification of structures resembling cellular membranes and organized carbon networks within meteoritic samples indicates that the chemical foundations for life can develop spontaneously in space environments. The potential for biological development within these cosmic environments extends beyond simple microbial life to more complex organizational structures. The vast internal volumes of larger asteroids could support biological communities with hierarchical organization, where different regions specialize in different metabolic functions while maintaining communication through chemical and physical transport mechanisms. The preservation of biological information over cosmic timescales within these frozen environments creates opportunities for the accumulation of genetic complexity that exceeds anything possible in more dynamic planetary environments. Biological systems could gradually accumulate genetic libraries that preserve the evolutionary history of entire ecosystems, creating molecular records of biological innovation that span the entire history of the solar system. The interaction between biological systems and the mineral environments within their host bodies creates opportunities for biomineralization and biogeochemical processes that might gradually transform the chemical composition of these biogeochemical composition. Cosmic objects. Over geological timescales, biological activity could create distinctive mineralogical signatures that would provide evidence for past or present life within these wandering worlds. The potential for biological systems to influence the physical evolution of their host bodies through processes like selective mineral dissolution or the production of organic acids creates feedback mechanisms where life actively shapes its environment over cosmic timescales. These biogeochemical processes might gradually create more favorable conditions for biological activity, leading to positive feedback loops that enhance the habitability of cosmic environments. The symphony of cosmic life. In the vast orchestration of the cosmos, where planets revolve in their stately dance and stars burn through their nuclear fuel across billions of years, the potential life within comets and asteroids adds a subtle but profound harmonia biological counterpoint that weaves through space and time, connecting distant worlds through the patient persistence of living systems adapted to the ultimate frontier. The rhythm of this cosmic symphony operates on multiple temporal scales simultaneously, from the rapid chemical reactions that might occur during cometary outgassing events to the geological pace of radioactive decay that maintains internal heat sources over millions of years. Each cosmic body contributes its own rhythmic pattern to this grand composition, its biological processes synchronized with orbital mechanics and thermal cycles that span decades or centuries. The melody of cosmic life emerges from the chemical conversations between different biological communities as cosmic bodies approach and recede from each other during their orbital journeys. These encounters create opportunities for biological communication across interplanetary distances, with chemical signals released during close approaches, carrying information about biological innovations and environmental conditions between widely separated populations. The harmonic structure of this biological network arises from the gravitational resonances that govern the long-term orbital evolution of asteroids and comets. These resonant relationships create stable pathways for biological exchange that persist for millions of years, establishing communication networks that span the entire solar system. The biological content of these cosmic wanderers becomes synchronized through these gravitational harmonics, creating coherent patterns of life that transcend individual worlds. The counterpoint of cosmic evolution introduces variations and innovations into this biological symphony as different populations adapt to the unique challenges of their specific environments. The chemical diversity of different asteroid and comet populations creates distinct ecological niches where evolution explores different solutions to the fundamental challenges of cosmic survival. These variations enrich the overall biological symphony while maintaining the underlying harmonic structure created by orbital mechanics. The dynamic range of this cosmic symphony spans from the nearly inaudible whisper of dormant biological processes during the cold phases of orbital cycles to the crescendo of activity that occurs during perihelion passages when thermal energy temporarily accelerates metabolic processes. These dynamic variations create a musical structure where periods of biological silence are punctuated by brief episodes of intense activity. The instrumentation of cosmic life includes the diverse metabolic pathways that different organisms employ to extract energy from their challenging environments. Radiotrophic metabolism provides a steady baseline of biological activity, while chemosynthetic processes create melodic variations that respond to changing chemical gradients. The occasional availability of liquid water during thermal events adds percussive elements to this biological composition. The tempo of cosmic life adjusts to the vast timescales available for biological development, operating at rhythms that make terrestrial biological processes seem frantic by comparison. Individual organisms might require centuries to complete single reproductive cycles, while evolutionary changes unfold over timescales that encompass entire orbital periods of the outer planets. This cosmic tempo creates space for biological innovations impossible under terrestrial conditions. The improvisational aspects of cosmic life emerge from the unpredictable nature of collision events, gravitational encounters, and other cosmic phenomena that can suddenly alter the environments within which biological systems operate. These cosmic accidents create opportunities for biological creativity and adaptation, introducing novel challenges that drive evolutionary innovation in directions that could not be predicted from the stable phases of cosmic existence. The ensemble playing of cosmic biological communities creates emergent properties that transcend the capabilities of individual organisms, establishing ecosystem-level processes that span the entire volume of their host cosmic bodies. These biological communities might develop collective behaviors and communication mechanisms that operate at scales measured in kilometers, creating superorganisms that exist at the intersection of biology and geology. The audience for this cosmic symphony includes not only the biological participants themselves, but potentially any intelligence capable of detecting the subtle signatures of life within these wandering worlds. The electromagnetic emissions, chemical signatures, and physical alterations produced by cosmic biological systems might eventually be detected by advanced observational techniques, revealing the hidden biological dimension of the solar system. The recording and preservation of this biological symphony occurs naturally within the geological structure of cosmic bodies, where the chemical signatures of biological activity become embedded in mineral matrices that preserve records of life across cosmic timescales. These geological archives create permanent records of biological innovation that could persist long after the organisms themselves have evolved beyond recognition. The universal themes explored by this cosmic symphony address fundamental questions about the nature of life, consciousness, and meaning in the universe. The existence of biological systems adapted to cosmic environments suggests that life is not merely a planetary phenomenon, but a fundamental aspect of cosmic evolution, a creative force that finds expression wherever chemistry allows and time permits. Now, rest in the gentle rhythm of this cosmic symphony, feeling the patient pulse of life spreading through space, carried by wandering worlds on journeys that span millions of years, creating connections between distant realms through the persistent creativity of biological systems. If this gentle vision of the cosmos soothes the mind, consider resting here more often. Subscribe to the channel and share your thoughts in the comments. A quiet echo beneath the stars, the eternal patience of wandering life. As consciousness drifts deeper into contemplation of these cosmic wanderers and their hidden biological treasures, there emerges a profound sense of the universe's infinite patience and creativity. The life that might exist within comets and asteroids represents the ultimate expression of biological persistence, existing in harmony with cosmic rhythms that span millions of years, while maintaining the delicate spark of organization that distinguishes the living from the merely chemical. These cosmic organisms would embody a form of existence that transcends terrestrial concepts of time and space, living through cosmic seasons measured in orbital periods, while maintaining continuity of biological information across timescales that encompass the entire evolution of planetary systems. Their lives would unfold according to astronomical calendars, with reproductive cycles synchronized to the gravitational dance of planets and the thermal rhythms of solar approach and recession. The patience required for existence in these environments surpasses human comprehension, representing a biological commitment to survival that spans geological epochs. Individual organisms might persist through millions of years of dormancy, maintaining their essential biological functions through metabolic processes so slow they operate at the boundary between chemistry and stasis. Their existence would represent the ultimate meditation on endurance and the preservation of life's essential spark through cosmic winters of unimaginable duration. The wandering nature of these biological systems creates a form of life that exists in constant motion through space, never bound to a single location, but always journeying toward unknown destinations. These cosmic nomads would experience the universe as a vast landscape through which they travel slowly, their biological awareness expanded across interplanetary distances, and their life cycles synchronized with the grand mechanical rhythms of the solar system. The community of cosmic life would exist as a distributed network spanning the entire solar system, with individual nodes connected through the patient journeys of asteroids and comets that carry biological information between distant regions of space. This network would operate as a single vast organism whose consciousness spans multiple worlds and whose memory preserves the biological history of the entire solar system across billions of years. The creativity of evolution in these extreme environments would produce biological innovations impossible under terrestrial conditions, exploring solutions to fundamental challenges of existence that transcend the constraints of planetary environments. The organisms that emerge from these cosmic laboratories would represent life's most creative responses to the challenge of survival in space, developing capabilities that bridge the gap between biology and technology. The meaning and purpose of cosmic life would emerge from its role as the universe's memory and communication system, preserving and transmitting information about cosmic conditions across vast distances and timescales. These biological systems would serve as living libraries that maintain records of cosmic history while slowly exploring the space of biological possibility through evolutionary experimentation that spans cosmic ages. The spiritual dimension of cosmic life emerges from its embodiment of qualities that humans associate with transcendence, infinite patience, cosmic perspective, harmony with natural rhythms, and persistence through conditions that challenge the boundaries of existence. These organisms would represent the universe's commitment to consciousness and organization, even under the most challenging conditions imaginable. The interconnectedness of cosmic life reveals itself through the gravitational and chemical interactions that link all wandering worlds into a single, coherent system. The biological content of one asteroid affects the evolutionary trajectory of organisms in distant comets through the slow mixing processes that operate over cosmic timescales, creating a form of distributed consciousness that spans the entire solar system. The wisdom that emerges from cosmic life transcends individual knowledge to become a collective understanding that encompasses the entire history and potential of biological organization in space. This cosmic wisdom operates through mechanisms of information, preservation, and transmission that ensure the accumulation of biological knowledge across geological timescales, creating a repository of evolutionary experience that grows richer with each passing eon. The beauty of cosmic life lies not in dramatic displays of biological activity, but in the subtle persistence of organization through conditions that seem utterly hostile to existence. The aesthetic of cosmic biology emerges from its harmony with astronomical rhythms, its patient adaptation to cosmic conditions, and its demonstration that life's essential creativity can find expression even in the most challenging environments imaginable. The hope embodied by cosmic life extends beyond individual survival to represent the universe's commitment to consciousness and organization as fundamental aspects of cosmic evolution. The existence of biological systems in space suggests that life is not merely a planetary accident, but a cosmic principle that expresses itself wherever conditions permit, creating a universe that tends toward awareness and complexity rather than emptiness and chaos. The mystery of cosmic life deepens rather than resolves as scientific understanding advances, revealing new questions about the nature of consciousness, the meaning of existence, and the relationship between mind and matter in cosmic contexts. These wandering biological systems serve as living koans that challenge fundamental assumptions about life while pointing toward possibilities that transcend current scientific paradigms. The legacy of cosmic life would persist long after its individual manifestations have evolved beyond recognition, encoded in the chemical signatures and mineralogical alterations that biological activity creates within cosmic bodies. These geological records would preserve evidence of life's cosmic dimension for future investigators, creating permanent testimonies to the universe's biological creativity that would survive for billions of years. The ultimate destination of cosmic life remains unknown and perhaps unknowable, but its journey reveals fundamental truths about the nature of existence and the universe's tendency toward complexity and consciousness. Whether these biological systems eventually seed new worlds, evolve into forms of cosmic intelligence, or simply persist as eternal witnesses to cosmic evolution, their existence transforms understanding of life's place in the universe. The contemplation of cosmic life creates a sense of kinship with these distant biological communities, recognizing in their patient persistence through cosmic challenges a reflection of the human commitment to survival and meaning in the face of overwhelming cosmic scales. Their existence suggests that consciousness and purpose are not limited to planetary environments, but represent fundamental aspects of cosmic evolution that find expression wherever conditions allow. The silence that surrounds cosmic life, the vast quiet of space through which these biological systems journey, becomes not emptiness, but a pregnant stillness filled with the potential for biological emergence and evolutionary innovation. This cosmic silence provides the acoustic environment within which life's most subtle melodies can emerge, creating biological harmonies that operate below the threshold of ordinary observation while maintaining the essential rhythms of existence. The eternal nature of cosmic life emerges from its synchronization with astronomical timescales that approach infinity from human perspectives, while remaining intimately connected to the fundamental processes that govern cosmic evolution. These biological systems exist at the intersection of time and eternity, maintaining temporal existence while participating in cosmic rhythms that transcend individual duration. Now, let awareness settle into the profound peace of cosmic time, where life moves with the patience of planetary orbits, where consciousness spans the distances between worlds, where biological communities persist through cosmic seasons that last millions of years, in perfect harmony with the fundamental rhythms of existence. The cosmic lullaby of deep space, in the ultimate reaches of contemplation, where thought itself begins to merge with the vast silence of space. The story of life on comets and asteroids becomes a gentle lullaby that carries consciousness toward the deepest rest. These wandering worlds, with their hidden biological treasures, drift through space like cosmic ships carrying the dreams of life across oceans of darkness, their patient journeys creating rhythms that soothe the mind into profound tranquility. The gentle rocking motion of asteroids and comets as they follow their elliptical paths through space creates a cosmic cradle that has rocked biological systems to sleep and wakefulness for billions of years. This astronomical lullaby operates on timescales so vast that entire civilizations could rise and fall within a single orbital cycle. Yet the biological passengers within these cosmic vessels maintain their essential rhythms through thermal cycles that pulse with the slow heartbeat of orbital mechanics. The whispered conversations between cosmic bodies as they pass through space carry messages of biological innovation and evolutionary discovery across interplanetary distances. These chemical communications travel slowly through the vacuum, carrying news of successful adaptations and biological experiments from one wandering world to another, creating a network of biological knowledge that spans the entire solar system, while operating at frequencies below the threshold of ordinary awareness. The dreams that might fill the consciousness of cosmic organisms during their extended periods of dormancy would encompass visions of thermal awakening, chemical abundance, and the brief periods of metabolic activity that punctuate their cosmic hibernation. These biological dreams would span centuries or millennia, filled with slow-motion scenarios of reproductive success and community growth that unfold at the pace of geological processes. The lullabies sung by cosmic radiation as it passes through space create gentle background melodies that have accompanied the development of cosmic life since the birth of the solar system. These electromagnetic harmonies carry information about stellar evolution, galactic rotation, and cosmic history, providing a constant source of gentle stimulation that might influence the evolutionary development of space-adapted organisms over cosmic timescales. The cosmic nurseries hidden within asteroid cores and comet nuclei provide the ultimate expression of protective environments where life can develop in safety while traveling through the vast emptiness between worlds. These internal sanctuaries shield their biological contents from the harsh realities of space while providing the chemical resources necessary for slow but steady biological development across cosmic ages. The bedtime stories told by the orbital mechanics of the solar system create narratives of gravitational interaction, resonant harmony, and the slow dance of worlds that has continued for billions of years. These mechanical tales describe the patient persistence of cosmic order through cycles of approach and separation, collision and dispersal that create the framework within which cosmic life can develop and flourish. The soft breathing of comets, as they release gas and dust during their approach to the sun, creates gentle exhalations that might carry biological materials across interplanetary distances, seeding new environments with the products of cosmic evolution, while maintaining the rhythmic patterns that have characterized these processes since the formation of the solar system. The twilight zones within cosmic bodies, where darkness gradually gives way to the dim illumination of radioactive decay, create environments of perpetual dusk, where biological processes can proceed at their own unhurried pace. These regions of gentle luminescence provide the perfect conditions for biological contemplation and the slow unfolding of evolutionary processes that require extended periods of stability and protection. The cosmic counting that marks the passage of time in these environments follows the rhythm of radioactive decay, orbital periods, and the gradual cooling of internal heat sources. This temporal music provides a steady pulse that has maintained its rhythm for billions of years, creating the metronome against which cosmic biological processes can synchronize their activities. The gentle gravity fields of asteroids and comets create environments where biological materials can drift slowly through internal spaces, following graceful trajectories that might take years or decades to complete. This low-gravity environment allows for biological processes that would be impossible under stronger gravitational fields, creating opportunities for three-dimensional biological organization that spans the entire volume of cosmic bodies. The eternal patience required for cosmic life creates a form of biological meditation that spans geological timescales, where individual organisms exist in states of contemplative awareness that encompass millions of years of experience. This cosmic mindfulness operates at frequencies so low that entire biological lifetimes might consist of single thoughts or simple metabolic processes that unfold with the deliberate pace of cosmic evolution. The protective embrace of cosmic ice and rock creates the ultimate expression of maternal care, where wandering worlds shelter their biological contents through journeys that span the entire solar system, while providing the chemical and thermal resources necessary for biological persistence across cosmic ages. These cosmic mothers carry their biological children through space with infinite patience and care. The starlight that filters through space provides a gentle illumination that connects cosmic life with the broader universe, creating visual links between wandering biological systems and the stellar communities that provide the energy for cosmic evolution. This distant starlight carries information about galactic processes and cosmic history that might influence the development of cosmic consciousness over astronomical timescales. The cosmic dawn that might eventually emerge from the development of space-adapted life would represent a new phase in cosmic evolution where biological consciousness expands beyond planetary boundaries to encompass interplanetary and, eventually, interstellar scales. This awakening would transform the universe from a collection of isolated worlds into a unified biological community that spans cosmic distances. Now, rest in this cosmic embrace, feeling the gentle motion of wandering worlds as they carry their hidden treasures through the vastness of space, drifting with them through cosmic time, where biological dreams unfold across millions of years, where consciousness expands to encompass the patient rhythms of cosmic evolution, where life persists with infinite patience through the eternal journey between worlds. Let awareness settle into the profound stillness of space, where time moves with the patience of orbital mechanics, where life exists in perfect harmony with cosmic rhythms, where consciousness drifts like stardust through the infinite darkness, carried by cosmic currents toward destinations unknown in the eternal dance of wandering worlds, through the vast silence of space, where every comet and asteroid carries within its heart the possibility of life, the hope of consciousness, the dream of biological communities that span the entire cosmos in perfect peace, perfect patience, perfect harmony with the fundamental rhythms of existence. Sleep now with the wandering whirl in their eternal journey through space, carrying the dreams of cosmic life toward unknown destinations, in the gentle embrace of cosmic time, where biological processes unfold with the patience of geological ages, where consciousness expands to encompass interplanetary distances, where life persists through cosmic winters that last millions of years, in the eternal lullaby of orbital mechanics, the cosmic cradle that has rocked the solar system to sleep for billions of years and will continue for billions more in the infinite patience of cosmic time forever and ever and ever. Amen.